Yes, sir.
So today we will see the concept of probability integration or the transformation by probability integration. Probability integral transformation. Earlier we have seen the transformation, it is based on the Jacobian approach. Now here we will discuss about the transformation based on probability integral. Consider a random variable x with distribution function df. The distribution of x is given by f of x, where we know that the CDF is lies between 0 to 1. Okay, we define an inverse function. It is not denoted as a f inverse x. Say y is equal to fx, which implies x equal to f inverse y. Okay, so that inverse function is exists. So what is the range of y? The range of y is 0 to 1, because we have equated y equal to fx, and the range of fx is 0 to 1, so range of y is also lies between 0 to 1. Okay, so let us say theorem. If x is a random variable with continuous distribution function fx, then random variable y is equal to f of x has a rectangular distribution over 0, 1. It is nothing but it is a standard uniform. So that means the y has the standard uniform distribution. If x is a random variable distribution, random variable with continuous distribution function is fx, then y is equal to fx is nothing but it has a rectangular distribution. Conversely, if y be a rectangular variable, rectangular means y is lies between 0 to 1 over 0 1, then x equal to f inverse fx inverse y has a probability distribution function fx. So if we are trying to find out the distribution of x, so what is the distribution of x? It is nothing but the fx. So what is given? X has distribution function, and we wish to show that the y has the rectangular distribution over 0 1. Conversely, if y is rectangular over 0 1, then we wish to show that x has the distribution function fx. So we know that the distribution function of y is written as fy of y is nothing but probability that y less than equal to y. So what is y? Because we know that y is equal to fx of x. Okay. So which implies if it is also given that fx is an invertible function, then can I write x less than equal to f inverse of x y? Okay, because f is a invertible function. Then it is a distribution function of fx, and the argument is f inverse x y. Okay, because we know that probability of x less than equal to x is nothing but fx of x. So here what is x? X is nothing but f inverse y. Because f is invertible, to fx of f inverse is nothing but argument itself. So f of y is equal to y. So we know that if y is distributed uniform or rectangular over 0 1, then f of y is nothing but 0 to y 1 dt. So it is nothing but dy. Okay, and so that is what it is saying, that this is the distribution function of y. It means that y is a uniform. That is, y is rectangular over 0 1. Rectangular distribution. So if part is over. Now conversely, what is given conversely? Y follows rectangular distribution over 0 1, or you can say y follows uniform 0 1. Then we wish to find out the distribution function of x. Then the distribution function of x is, so how will you write f of x is equal to probability of x less than equal to x. But we know that what is, we know that the y is equal to fx, which implies x equal to f inverse y. Okay, we know this. So we just substitute here. It is a probability that fx inverse y is less than equal to x, which implies, because y is invertible, so can we write probability of y less than equal to fx of x? Can we write? And because we know that what is the distribution of y? It is a 0 to 1. So what we can write? What is the distribution function of probability of y less than equal to y? It is a y. Okay. So what is the y? Y is nothing but fx. So because probability of y less than equal to y is equal to y. Okay. And we know that y is equal to f of x. That is how we have written. So what it's showing? We wish to find out the distribution function of x. Okay, the distribution function of x is nothing but what I will get? I will get finally fx. Fx of x is a distribution function of x. Okay. Any questions? Anyone? So this theorem is over. The transformation, whatever transformation we have applied, transformation y is equal to fx is known as probability integral transformation. Okay, so we are using the concept of this distribution is nothing but concept of the probability. So it is a probability integral transformation. And yesterday, if you remember, we have used this particular transformation to generate a random numbers from exponential distribution. So we know that what was that? F of y is equal to e raised to, suppose let us say lambda into e raised to minus lambda y, where y is lies between, or y is greater than 0, lambda is greater than 0. So what is the distribution function of y? It is nothing but it is a 1 minus e raised to lambda y. So now we have compared the uniform random numbers because the range of this is from 0 to 1. Okay, and uniform random numbers is also lies between 0 to 1. So therefore, what is we get? We get we can compare u equal to fy. So what you will get? U is equal to, what is fy? It is a 1 minus e raised to minus lambda y. So which implies y is equal to minus 1 upon lambda log of 1 minus u. So this is what yesterday we have obtained. Okay. So the relation between u and y is this. Suppose instead of u, if you say that x is a uniform random number, then here you can write a x. Okay. And this we can use, if given a value of u, we can easily calculate the value of y. Now let me take one more example. If, okay, x1, x2, xn are random sample drawn from continuous uniform 0, 1. That means x1, x2, xn are random sample drawn from uniform distribution, standard uniform. Show that z is equal to minus 2 log I running from 1 to n log xi has a chi-square with 2n degree of freedom, chi-square distribution. Okay, so what is given? We have given that xi's are, or we have given that xi's are random sample from uniform 0 to 1, where I range from 1 to n. So that means what is the distribution of f of xi? Is xi. Okay, I running from 1 to n, because uniform has the density is fx equal to 1 when x is lies between 0 to 1. So what is the distribution? Fx is nothing but x. Now, what is, let us say y is equal to minus twice of log x. Y equal to. Why we are saying that? That is y. We'll use suffix later. Okay? Because here the twice into log x is given. So I say them it is a y. Which implies what is the distribution of x? X is equal to, this is minus y by 2, and that is e raised to minus y by 2. So x is nothing but minus y by 2. Here what is the range of x? X is, if you substitute x equal to 0, what happens? Log 0 is minus infinity, so it is a positive. So y becomes the infinity. And if you substitute x equal to 1, log 1 is 0. So that means the range of y is greater than 0. It lies between 0 to infinity. Okay. So if we take the just transformation, or you can just take the derivative both the side, dx is equal to e raised to minus y by 2 into minus 1 by 2 dy. So it is nothing but minus half of e raised to minus 1 by 2 dy. Therefore, what is the distribution of fy of y? It is nothing but, what is the distribution of y, or the PDF of y? We have given what we have given. It is nothing but fx of g inverse y. This we know, na? Into the Jacobian of del x by del y. But here what happened? Fx itself is a uniform. So fx of this is nothing but 1. And Jacobian of this is minus half of e raised to minus 1 by 2. It is a half of e raised to minus y by 2. Okay. So this is a density of what? Which shows that y is distributed with chi-square with 2 degree of freedom. What is the degree of freedom? It is a chi-square with 2 degree of freedom. Okay. Here x1, x2, xn are IID. They are random sample, that means they are IID. Okay, that means y1, y2, yn are also IID, because if the x x1, x2, xn are, you can have this, so you can have the corresponding y1, y2, yn. Okay, so if x1, x2, xn are independent, then of course the y are the function of the variable, so they are also independent. So we know that all yi's are distributed chi-square with 2 degree of freedom, I equal to 1 to n, and yi's are independent. Okay, therefore z is nothing but minus twice of summation I running from 1 to n log xi is nothing but it is a summation I running from 1 to n yi. Okay, because you have taken y is equal to minus 2 log xi. So yi's are independent chi-square. So we know that property of additive property of chi-square. Distribution. If y1, y2, yn are independent chi-square, are independent chi-square with 2 degree of freedom, then their sum z is equal to minus I running from 1 to yi is independently distributed as chi-square with the sum of degree of freedom. So how many times 2 is repeated? N times. So that is the degree of freedom is 2n. So that is what we wish to find out. Show that it has a chi-square with 2 and degree of freedom. Okay. Any questions? Anyone? If no question, then there is an example. It is in the homework. Let x1, x2, xn are random sample from a uniform distribution find the PDF of u equal to x1, x2, xn raised to 1 by n. Okay. So this is the homework, and you can use the as a hint. Z is equal to minus twice of summation I running from 1 to n log xi is chi-square 2n. That we have already proved. Okay. And if you take the log transformation, let us say u, then x1, x2, xn raised to 1 by n, then what happen? Log u equal to 1 upon n summation log xi. Okay, so it means that what is the distribution of log xi from this? That you have to use this result, and if based on this you can calculate the distribution of this. Okay, so this is the homework. You can easily calculate, there is no issue for you. Or you can also use in this way. There is also the, if you don't want to do this, you can write in this form. What is, it is a minus z by 2 is equal to summation I running from 1 to n log xi. Okay, so is equal to, you can write it is a log of x1, x2, xn. Okay, these are all in the product. Can we write? So which implies the joint product that is I would equal to 1 to n xi. It is nothing but x1 into x2 into xn is equal to e raised to minus z by 2. So you can use also this. Somewhere something either you can go in this way or by using this you can try to solve this result. Okay, and I will give you the PDF. The answer I will give you, the PDF of u is nothing but n raised to n u raised to n minus 1 upon gamma n log 1 by u raised to n minus 1 u, where u is lies between 0 to 1. Okay, so this is the answer. So you can try at the home. Now suppose we have given function of two random variables and we wish to find out their joint distribution. Then how to give? So we have used the technique of transformation of variable, but this is the another way you can obtain the function of two random variables or the joint density of the two random variables using the probability integral transformation. So this function of two random variables using distribution function approach. I will give you directly the result. You have to use that result to solve the examples. Let xy be two joint continuous random variable with PDF fxy of xi small. Then find the distribution u equal to x plus y, v equal to x minus y, 3, w equal to xy, 4, z is equal to x by y. So suppose if I wish to find out the distribution function of u, so u is nothing but it is a sum of two random variables, v is a subtraction of two random variables, w is a product of two random variables, and z is equal to ratio of a two ratio of two random variables. Okay, so ultimately we wish to, because if I'm interested to find out the distribution of u or PDF of u, PDF of v, PDF of w and z, so I have to find out the marginal density. Okay, so I'll give you the direct results. So we have to use that results. There are theorems. Let xy be jointly distributed random variables with PDF fx y of xy, then the PDF of u equal to x plus y, v equal to x minus y are respectively given by f of u equal to u is nothing but this integration of minus infinity to infinity f of x y x u minus x dx, because I'm interested to find out the I'm interested to find out the density of u, so I have to integrate over the x, so I can get the density of u. Or if you wish to write in the form of function of y and u, then it is something like that: f of x y u minus y and you integrate over y. So if you use this, you can easily get similarly f v of v is nothing but, you have to remember these results. That results will useful to fxy of x minus v. Okay, because x plus y, if u equal to x plus y, then what is y? Y is equal to u minus x. And if u equal to x minus y, then what is the y? It is x minus u. Okay, likewise, and integrate over dx, or you can write in the form of the y, it is a v plus y dy, because v equal to x minus y. Okay, then what is the x? So if you take the y on the left hand side, so it is a v plus y is equal to x. So this is the, and if corollary, if x and y are independent, this is giving the, if x and y has no condition is given, x and y are jointly distributed is given, just you have to substitute wherever the y, you have to substitute it by the u minus x and take the derivative, sorry, integration over the x, you will get the density of u. Or if you are using this form, then wherever there is x, you can substitute u minus y. In this setup, similar way you have to do. But if we given that x and y are both independent, continuous, random variables, the PDF of u plus y, so the PDF of x plus y and x minus y are respectively given by, so what was the form? F of u is equal to u. Here it is nothing but they are in the joint. So because x and y are independent, so you can write it is a marginal of each, that is fx of x and fy of u minus x. So it is nothing but integration of minus infinity to infinity fx of x into fy of u minus y and integration over the dx. And if it is in the form of the integration over the y, then it is nothing but fx of x minus u. Is it? Or u minus y? Let us see. Sorry, it is a u minus y into fy of y dy. And second, f v of v is nothing but integration of minus infinity to infinity. So what is that? It is a fx of x and fy of x minus v. integration over dx. And if we are talking of the integration over dy, that is the fx of x plus v. You can see here it is fx of, sorry, y plus v plus y, not v plus v plus y into fy of y dy. Okay, so this is the some form that you have to remember. I'll give you the example that you have to do at the homework. Suppose x and y are independent uniform 0 1, then obtain PDF of u is equal to x plus y, v is equal to x minus y. Okay, here, okay, so this you have to obtain. So whenever the x and y are independent, then whatever the density you have written, this is FUU or FPV, is called convolution of the densities. Convolution of densities with density fx and fy. Okay. I think you can solve. These are all the at the BSc level. You have solved many examples. You can easily work out on that. We will take another theorem again without proof. Let x, y be jointly distributed continuous random variables with PDF f of xy, xy, the PDF of w is equal to xy and z is equal to x upon y. We have already seen the, if I wish to find out the sum of the random variables, okay, using the transformation of variables. So what we do, we let us say u equal to x plus y and v equal to y. Find out the Jacobian and then solve. Okay. Similarly, if you wish to find out the, let us say z is equal to x by y. Okay, then take the another variables w or the y is equal to y. So it is a just transformation of the two variables, and based on that you can easily calculate the density of u, v, w, z something. But if you don't want to go for that, and if you wish to find out the density based on the distribution function approach, then these results are useful. The density of w is nothing but it is integration over minus infinity to infinity absolute value of x fxy x w by x, and it is integrated over dx. Or in the form of y, it is a 1 of absolute y f xy is nothing but wy by y. Why? Because w is equal to x by y. So if you are making the x as a equation maker, then x is equal to w by y. Okay, so wherever x, you can substitute w by y. But if you wish to make y the equation maker, then y is equal to w by x. So you have to substitute y equal to w by x. And what is the Jacobian of w by x with respect to w? It is a 1 by x. So that is how it is written. And if you wish to find out the z is equal to x by y, then the density is nothing but integration over minus infinity to infinity. Here the range is of, here I have taken in general setup minus infinity to infinity, but I have to see the what is the range of x. That range I have to supply. What is the range of y? That range I have to supply. So it is nothing but 1 upon, not 1 upon, because it is a division is there, so it is in the multiplication. It is a y into fxy yz y dy, and it is given that, provided that probability of y equal to 0 is 0. That means y cannot be 0. It is that probability that y equal to 0. Why it is so? Because here you have a z is equal to x by y. So just you can write in this form of x equal to zy. So wherever, and what is the derivative of x with respect to z? It is a y. So I have just written here y. And wherever the x, I will just substitute the zy. And then I have to integrate over the dy. I will get the marginal density of the z. Is that okay? Any questions?
Yes.
Anyone?
No, sir.
So same example again. It is the homework. xy follows. Okay. Let me and whatever the examples I am giving, that you have to solve as a form of the part of assignment. Okay, because there are 5 marks for the assignment. So whoever is submit the example according to that, they will get the marks. So whatever the discussions are taking place simultaneously, you have to solve the example. X and y are independent variables each uniform over 0, 1. That means x and y are independent random variables and they are uniform. Then find PDF of w is equal to xy, and second z is equal to x by y. So if they are independent, then what you can write, this PDF can be written in the form of, okay, if they are independent, what will you write? W, PDF of w is nothing but, it is a minus infinity to infinity 1 upon absolute value of x, f of xx, and f of fy of w by x. Okay, and you just take integration over dx, or you can write minus infinity to infinity 1 upon absolute y f x of y by w or w by y into fy of y integration of dy. So what do we know that? We know that the x and y are uniform 0, 1. Then the PDF of x is uniform, okay, and PDF of y is also a uniform. So the PDF uniform is, that means it is taking the 1, it is also taking the 1. So it is the integration of 0 to 1 by x dx. And what, when you solve it, you will get the answer. Make sure that you have to see the range, because if you are finding the w equal to xy, then what is the range of x? It is a w by y. Okay. So then the x is lies between w to 1. So just integration over that, you will get the answer. Similarly, fz of z is nothing but it is integration over minus infinity infinity absolute value of y fx of yz into fy of y into dy. Okay. So this is the things we have. We can have the density of yz. Here again, we have a uniform, and based on that, you can just substitute divide, take the integration of y over the dy, and what is the range of y? The range of y is, because z is equal to what given? It is a x by y. So which implies y is equal to x by, sorry, y is equal to x by z. Okay, but what is the range of x? So x is from 0 to 1. Okay, so what is the range of y? The range of y is that lower limit is x by z and upper limit is maximum is 1. So that you have to integrate over the 0 to 1 by z 1 dy, or sorry, y dy. So it is giving the answer, that is y square by 2, and here 0 to 1 by z is a, what is the answer? It is a 1 upon 1 by z square by 2. It is nothing but 1 by 2z square. So that is where you can find out the density of w and z. So you have to just substitute it and see the what is the range of y. So based on the relation that you have to. Okay. So any questions, anyone? Okay, so if no questions, I think this part will over here. You can also try the transformation of variables by taking the different density. Now I will discuss the another methods. That orthogonal transformation. We have seen the transformation variable. In transformation variable, suppose we wish to apply the orthogonal transformation, then how to apply? What do you mean by the orthogonal transformation? And what do you mean by the incomplete orthogonal transformation? So I'm just giving that concept, orthogonal transformation. So we all have studied at the graduation level when we say that the two vectors are orthogonal to each other if the vector itself multiply with the vector result is 1 and vector multiply with the others then the result is 0, then we say that two vectors are orthogonal to each other. Okay, so similarly if the two matrices are orthogonal to each other then we say that the let us say C is a matrix which is orthogonal, then we say that C transpose C is equal to identity. Okay, and we know that what is the determinant of C? It is a 1. Why? Because the identity matrix determinant is 1. So then we say that it is a orthogonal. Sometimes we write that C dash C equal to CC transpose. So what it means? We say that C is a complete orthogonal. So here we will discuss what do you mean by the complete orthogonals and what do you mean by the incomplete orthogonal transformation. Okay. Let x1, x2, xn transpose. So that means let x1, x2, xn is a column vector. And let x equal to and let y equal to y1, y2 up to yn transpose. A linear transformation y is equal to cx. So we know that if x is a normal, then the linear function of x is also a normal. So orthogonal transformation is mainly used when your distribution is of a multivariate normal, bivariate normal. Okay. So at that time we mainly use this. A linear transformation y is equal to cx is said to be orthogonal if C is orthogonal. So linear transformation is said to be orthogonal. When it is said to be orthogonal? When C is orthogonal. So what do you mean by the orthogonal? That is C transpose is equal to identity. So if let us say if I am writing y is equal to C x. So what is the order of n? X, it is a n cross 1. Order of y is n cross 1. It means the order of n is n cross n. Sorry, order of C is n cross n. Okay, so that means C is a n cross n square matrix. And all x is transformed to the y. That means none of the x is remain here because the how many variables in the vector y? N. And how many in the x? It is a x. N. Okay. Further, determinant of C is 1. That is, determinant is not equal to 0. That is, C matrix is a non-singular. That is, C is a non-singular matrix. Okay. Also, you can note that you have that C dash is equal to identity. So if you pre-multiply, because it is invertible, then inverse is exist. If you pre-multiply this by the C inverse, then you can have this. But what is the C inverse C? It is a identity of order n into C dash. It is a C inverse. So anything multiplied by the identity matrix, it is a matrix itself. So C inverse equal to C dash. So in when there is a C is orthogonal matrix, we say that to find out the inverse, it is to just take the transpose of the matrix. Okay. Similarly, C transpose C is equal to, because C is a square matrix, we can write C transpose C equal to C transpose is equal to I, because C is square matrix. Okay. So just pre-multiply by the, okay. So what do you get? You can just pre-multiply by the C. So C transpose C is equal to C into I. So what will you get? Because C transpose is nothing but C inverse. Okay. So this is nothing but identity to C equal to C. So it means that when your C is a square matrix and CC transpose is equal to identity, then you can write C transpose C is equal to CC transpose. And determinant of C1, then C is a orthogonal matrix. So when it is orthogonal matrix, we know that when I'm writing x equal to x1, x2, xn, and y equal to y1, y2, yn, then what is the C? So if I'm writing the C as a C11, C12, C1n, C21, C22, C2n, Cn1, Cn2, Cnn. So what is the y is equal to Cx? It is nothing but, can I write? Okay, I will show you. C11, C12, C1n, C21, C22, C2n, Cn1, Cn2, Cnn. This is a x1, x2, xn. So what will you get? First row multiply by this column. It is a C11 x1 plus C12 x2 plus up to C1n xn. So what is the second row? It is a C21 x1 plus C22 x2 plus up to C2n xn. And last is a Cn1 x1 plus C2 n2 x2 plus up to Cnn xn. It is nothing but summation j equal to 1 to n P1j xj. Similarly, summation j equal to 1 to n P2j xj, and summation j equal to 1 to n Pnj xj. So it is a likewise you can have. So it means that yi is equal to, suppose if you talk the ith row, then it is nothing but j equal to 1 to n Pij xj, I equal to 1 to n. Okay. So whenever you apply the transformation y is equal to cx, where C is orthogonal and square, then we say that it is a complete orthogonal transformation of x on y. Let x1, x2, xn be IID normal 0, 1. Then, okay, and, not then, and yi equal to j equal to 1 to n Tij xj. Then what are the properties? See, orthogonal transformation is a beautiful transformation. Whenever you observe that x1, x2, xn are the standard normal variate and they are IID, okay, then if you apply the orthogonal transformation, there are certain beautiful properties. So here the yi is nothing but orthogonal transformation of x, x, okay. Then the first property is that y1, y2, yn are also IID 0, 1. So if x are normal 0, 1, then y's are also normal 0, 1. If x are independent, then y's are also independent. Why? Because ultimately the aim of the orthogonal transformation is that whenever the x are dependent variables, if you wish to convert or we wish to find out the some vector of independent variables, we can apply the orthogonal transformation. And this mainly you will use when you come to the semester 4 and when you study the principal component analysis and factor analysis, where we apply the orthogonal transformation. In second semester, when you are getting the problem of multicollinearity, so again, to obtain the independent vectors, we can use the orthogonal transformation. So if x are IID normal 0, 1, then the orthogonal transformation variables yi are also IID normal 0, 1. Another thing is that x dash x equal to y dash y. That is, x dash x is nothing but the summation xi square I equal to 1 to n is equal to summation yi square. So if you take the transformation, the summation xi square is also equal to the summation yi square. So here you can show how it is. Y transpose y. What is y? Y it is a cx. Cx transpose cx. Okay, that means you can write x transpose c transpose cx. So what is the C transpose is nothing but inverse. So C transpose C is the identity. So X transpose I X, and that is nothing but X transpose X. So Y transpose equal to X transpose X, and it is nothing but the summation Xi square by into equal to summation Y square. We all know that X transpose X is nothing but X1 up to Xn, and X is nothing but X1 X2 up to Xn. So it is nothing but x1 square plus x2 square plus up to xn square, and is nothing but the summation xi square. In distribution theory, your matrix algebra should be good. So even whenever you wish to go for the next semester multivariate analysis, again your matrix algebra, your Jacobian, your derivatives, integrations, this are also should be good. Okay. If elements of C, earlier what happened, we have simply said that C is a non-singular matrix. We have not said whether the C is a elements of C are random or the fixed. So here we have not give any comment on that. Okay, if we take purely real numbers, then what happen? If they are random, then what happen? If the elements of C are random variable, then the transformation is called random orthogonal transformation. In this case, the conditional distribution y1, y2, yn given C is normal 0, 1. Okay, so what we have to make here, if let us say C is a n cross n matrix and it is a orthogonal matrix and all the elements are real, okay, then real and fixed, then you can whatever the transformation you are using, that is said to be orthogonal transformation, and it has these two properties. If x1, x2, xn are random, normal 0, 1, then y1, y2, yn are also a random normal 0, 1, and the summation xi squared is equal to summation yi squared. But suppose if the elements of C are the random variable, then whatever the transformation you use, it is called random orthogonal transformation. And again, if you wish to find out the distribution of y1, y2, yn, then what happens? If there are two random variables, so we have to conditioning the one. So we will keep C as a conditioning and then try to find out the density of y1, y2, yn. Then it is a normal 0, 1. Okay. If the conditional distribution does not depend on the conditional variable, suppose y1, y2, yn are free from C. So that means the conditional distribution of y1, y2, yn does not depend on the conditional variable. Here conditional variable C. Then the variables y1, y2, yn are unconditional or absolute. Okay. Is that clear? So complete orthogonal, when we say that the complete orthogonal or orthogonal, when x is some vector given, it is of order n cross 1, C is a matrix of order n cross n, which is a non-singulars, which is orthogonal matrix. It is of order n cross n, such that the determinant is 1 and C transpose is equal to identity or is equal to C transpose C. Then the transformation y is equal to Cx is known as a complete orthogonal transformation. And if the element of the C matrix are random, then you have to obtain the distribution of y conditioned to the C. Okay. Then it is said to be a orthogonal transformation, or a random orthogonal transformation, this is said to be a complete orthogonal transformation if the element of C are not random. So now we will talk about incomplete. So what is the difference between the complete orthogonal transformation and incomplete orthogonal transformation? When I am saying that complete, it means that the C matrix is square matrix. But suppose C is a rectangular matrix, then you cannot transform all x into the orthogonal variables y1, y2, yn. Some of the are untransformed variables. So we will talk about incomplete orthogonal transformation. Let x1, x2, xn are IID normal 0, 1, and if C1, instead of C, I am saying that C1 is an orthogonal matrix such that C1 transpose is equal to identity of order M. Okay, that means what is the order of C? C1 is order of M cross N. So that C1 transpose is N cross M. So here you can see that the column multiply with the row. Okay, when you are saying that complete orthogonal, it means that if you multiply row with the row, it is giving identity matrix. If you multiply the column with column, it is giving the identity matrix. But in incomplete orthogonal, it is not the case. You can just multiply the row with the column, then it is giving the identity matrix. But you cannot multiply the column with the row, it is giving identity. So it is only one side identity. It doesn't mean that you can write the C1 transpose C1 equal to identity. Then y is equal to C1x is called incomplete orthogonal transformation. Okay, and it has the properties. First, y1, y2, yn are independent normal 0, 1. So if x1, x2, xn are independent normal 0, 1, this property remains. Y1, y2, yn are also independent normal 0, 1. But earlier, whatever we say that x transpose is equal to y transpose y. But here it is not the case. You cannot write the x transpose x is equal to y transpose y. But you can say that z is equal to x transpose x have how many variables? N variables. So it is a summation xi square. And you have transformed only m. M is nothing but less than n. So how many variables you have transformed into the orthogonal m variable? So what about the last n minus m? So that is summation xi square minus summation yj square, or you can say that x dash x minus y dash y. So they have the they have the chi-square with n minus m degree of freedom. And third, y1, y2, yn, y1, y2, ym. Here it is a m, not the n. y1, y2, ym and z are independently distributed. what is the addition here? Earlier, what happened? If x1, x2, xn are IID normal 0, 1, so we have a all the variables are transformed into the orthogonal variable. How many variables? It is a n variables. So it is a y1, y2, yn. But in incomplete, you are not transforming all variables. How many variables you are transforming? Let us say the m variables. So y1, y2, ym are independently normal 0, 1. So what about the rest of non-transform variable? Total variables are here xi I running square, that is I running from 1 to n. So there are n variables. And here how many variables? It is m variables. Because y1, y2, ym has the normal 0, 1, then what is the distribution of yi square? It is a chi square with 1 degree of freedom. So what is the summation of yi square? It is I running from 1 to m. By additive property, it is a chi square m. xi square having a normal 0, 1. They are independent. Then how many observation? There are n. So summation xi square having a chi square with n degree of freedom. So if you take the difference, summation xi square I equal to 1 to n minus summation, let us say j equal to 1 to m yj square. Okay, so here how many? N. Here having m. But these two are independent. So that means it has the chi-square degree of freedom, chi-square distribution, and the sum of the corresponding degrees of freedom. So here it is a n, and here it is a this. So it is a chi-square with, and that is now z. But these z's are independent with the y1, y2, ym. So when incomplete transformation is useful, whenever you are finding the in regression theory beta 0 plus beta x plus epsilon, and if you write in the form of the matrix notation 1x beta 0 beta 1 plus epsilon, okay, and if this is the yi xi epsilon I, then this is epsilon 1 epsilon n, okay, this is the case 1 1 1 1, this is the case x1 x2 xn. So it is a y is equal to x beta plus epsilon. So whenever you wish to find out the testing of beta equal to 0, you have to use the concept of ANOVA. And in ANOVA, this is called estimation part and this is called the errors part. These both are orthogonal to each other, and distribution of this part we will obtain as a SSR beta, and this is a SSE, and where we use this result, the SSR and SSE are independently distributed and they are chi-square. The ratio of 2 chi-square divided by degree of freedom follows the F. So this incomplete transformation will be used also in that. Any questions, anyone?
No, sir.
Okay, if no questions,